I'm going to see how far I can get with my voice. I just about burned it out yesterday. So if I lose it, we'll just stop. We're going to begin looking at the lithosphere. We're talking about oceans. We looked at the oceans of magnetism around the Earth called the magnetosphere. And we looked at the atmosphere underneath that and talked about all the different meteorological phenomena. And then we dove into the hydrosphere, the oceans, and talked about some of the basic characteristics, the surface currents, deep currents, what's happening at the poles, and so on. We'll come back and talk a little bit about the ocean when we get to rivers, because there are rivers in the ocean. Now we're going to look at the ocean of rock under our feet, the lithosphere. Under our feet, there are basically three different units. You can see them here. The surface crust is called the lithosphere. It's broken up in a series of plates, and geologists believe that they bump into each other and slide under each other and move around in a process called continental drift. Underneath that is the asthenosphere. In Greek, astheno means weak. So it's a weak sphere. It's weak because it gives, it moves. It's like a plastic, like silly putty or like taffy, that moves very slowly like a slug and carries the plates on its back. Underneath that is a solid core of iron and nickel. At least the inner part's solid, the inner core. The outer core is believed to be molten iron and nickel. In the 1970s, there was a meteorologist named Alfred Wegener who believed that the continents fit back together at one time. Evidently, he was very good at jigsaw puzzles, because whenever he saw the continents, he saw that they were like pieces of a puzzle. And so he cut them out and arranged them into a massive continent called Pangaea, which means all lands. What was interesting is not only did the puzzle pieces fit back together, but the picture was the same. If you're ever doing a jigsaw puzzle and you can find pieces that fit perfectly, but you know they're the wrong pieces because the picture doesn't match across the breaks. Well, the picture matched. You can see the black dots there. They represent coal deposits. And then the yellow areas represent sand dunes. And so what he was seeing across Pangaea was what they call a paleo equator. The equator, we had the rainforest with lots of vegetation that creates the coal deposits, and then the low latitude deserts to the north and south that create the dune fields. And so as other information began to combine over the next several decades, plate tectonics began to be widely accepted, that the continents did drift. Along with the theory of continental drift that Wegener proposed, there was another geologist named Harry Hess who proposed that the seafloor actually spreads, it opens up. And so combining seafloor spreading and continental drift, we come up with plate tectonics. And over the last 50 years or so, they've done quite a bit of detail of mapping out the movement of these continents. So this is a recreation of what Pangaea may have looked like, and you can see it breaking up to a series of images, and the seafloor, which is the Atlantic, is opening up. As the Atlantic opens up, North America is being pushed to the west. And so this is North America as it's developing. You notice that as it develops, there's a seaway that forms. There's a seaway that forms down the center of the continent, right here. It extends all the way to the Gulf of Mexico. So we went back to the Cretaceous during the time of the dinosaurs. The Gulf of Mexico would extend up to where we are in Dallas. That's one of the reasons if you go out near Red Oak, there's some road cuts there. If you look in the rocks, the Cretaceous rocks, you can find shark's teeth. So the question is, what in the world are sharks doing in Dallas? Well, plate tectonics will explain that. When the sharks were alive, there was an interior seaway and they were swimming through the middle of the United States. Now, keep in mind, this is all hypothetical. This is all theory, but it's a powerful theory because it explains these types of anomalies. The earthquake distribution is along these plate boundaries. In other words, earthquakes do not occur randomly on the Earth's surface. They occur along very specific seismic zones. And geologists are convinced that that's marking out the edges of these plates. That's where they bump into each other and rub against each other and create tremendous stresses and strains. There's a tremendous amount of earthquake and volcanic activity along the Pacific Rim. This is the Pacific Ocean. You can see all the earthquakes along the edges. And the reason is they believe that the lithosphere, the plate of the Pacific Ocean, is being subducted. It's being pushed back into the interior. As the Atlantic opens up, it's pushing the continents over the Pacific. And so as it's inching its way back into the Earth's interior, is creating all this stress and strain, and what geologists call the ring of fire. It's called the ring of fire because there's also volcanoes, tremendous volcanoes in this area. And the volcanoes come from the melting plate as it goes back into the Earth's interior. This is just a diagram showing all the different plates. Some of them are very large. Some of them are quite small. It's like the shell of an egg that's been broken. And about the same dimensions when you consider the lithosphere compared to the size of the Earth, about like an eggshell. Down the middle of the Atlantic Ocean is a mountain range. We've known about it for quite a while because we have sonar, and we've mapped the bottom of the ocean by bouncing sound waves off the bottom. However, in the last 50 years or so, we've developed deep submersible submarines that can go to the bottom and take pictures of it. But there's a mountain range that runs down the middle of the Atlantic, and right in the middle of that mountain range is a deep valley, a rift. The way that geologists fit that into the plate tectonics model is they believe there's a plume of hot material, a fountain of hot material that's coming off of the core through the asthenosphere, and when it hits the base of the lithosphere, it heats it up. And when things heat up, they expand. We've seen that before. And so as the rock expands, it lifts up the ridge. And the movement of material to either side is actually creating an extensional force that's pulling it apart. And that's what creates the crack in the very top, which is the rift valley. As this mantle plume moves to either side, it carries the oceanic lithosphere piggyback style. And then eventually it hits the edge of the continent and it's subducted back into the interior. And when those two plates rub against each other, that's where all the earthquakes are occurring. This is another diagram showing seafloor spreading. You have the oceanic ridge, you have the movement of the asthenosphere, you have the subduction here. You can see as the material is pushed back into the Earth's interior, it heats up. And as it heats up, material melts off of it like chocolate and rises to the surface. You can think of the oceanic plate sort of like a chocolate chip cookie. You have two types of material, of high silicate and low silicate material. When I say silicate, it just means glass. So high silicate means it's very glassy. Low silicate means it's not very glassy. Well, glass melts at a very low temperature, so it's like chocolate. And so as this chocolate chip cookie is pushed into the interior, the chocolate melts and rises, and the cookie goes on down into the interior. Since the chocolate is high in silica, as it's embedded into the continent here in volcanoes, it makes the continents more and more silicate, rich, more glassy, and they also get thicker. And that's what eventually caused them to stick above the ocean. It's because of how thick they're getting with the injection of all this chocolate or silicate. When you look at the age of the ocean floor based upon dating of the rocks are younger near the ridge system and get progressively older as you move away from the ridge, which is what they would expect with seafloor spreading that Henry has. Matter of fact, this is one of the leading evidences that he used to suggest that the seafloor is spreading. The seafloor spreads and it carries the continents with it, pushes the continents aside. Polarity reversals. We talked about the Earth's magnetic field and how it shifts back and forth. When you look at the polarity of the rocks on the ocean floor, you also see this striping that's typical of seafloor spreading, this symmetry that you see on either side. See how you see the two bands there and the two bands here? You can match it all the way across. It's like looking at a mirror because rock is moving to either side at the same speed, and it's making a duplicate. It's essentially a magnetic tape. It's a basic principle of like an 8-track tape or a cassette tape where you superimpose a magnetic field on the materials inside of that vinyl. And so God has placed if they're right, God has placed a magnetic recording of the polarity reversals on the bottom of the ocean. It's just kind of cool. You see technologies all through nature. It's almost like God is saying, oh, you did that? I've already done it. Like someone invents a spear. God already invented spears with spear grass. Someone invented the fishing pole. God already invented the fishing pole. He put it on the head of a fish, an angular fish, a fish that fishes. You've heard of fiber optics. There's a mineral that has fiber optic qualities. So we shouldn't be shocked to find a magnetic tape recording on the bottom of the ocean. What's happening at the very center of the ridge system is molten rock called magma is being injected into this fracture as it's pulled apart. And then that rock crystallizes and forms like a patch. But this extensional forces continue and it pulls the patch apart right down the middle. And then another patch forms, and then that's pulled apart, and another patch forms. And so it's this continuous patching that's going on here. And that patching of materials what creates the oceanic floor. When we drill into the oceanic floor and look at it, it's called a sheeted dike complex. It's sheeted because it occurs in vertical layers like sheets. And whenever material is injected vertically, geologists call that a dike. This is a dike that occurred off of a volcano in New Mexico. You see the layers in it, how they match each other. This formed in a similar way as the magma moved into this area, it pulled the earth apart, created a crack. That crack was full of molten rock that crystallized. Then the extension continued and pulled it apart. So this was once a patch. That layer and this layer, they were pulled apart and new material was injected in between it. Then that was pulled apart and new materials injected in that. And it would have kept going. It would pull that apart. So eventually you would have an ocean of sheeted dikes. When our deep submersibles went to the bottom of these rifts, they found a spring, a hot spring, and they call it a black smoker. It's called a black smoker because the sulfides and the manganese that's coming out of the rock creates a black appearance to the water. But it's a hot spring. And they exist at the bottom of these rift valleys where the earth is being pulled apart. Black smokers. The towers on them can get up to 12, 13 feet high as the sulfides form tubes, essentially.
Solidify. Clouds of sulfides solidify into towering chimneys as tall as a 3-story house. At 400 degrees, this scalding cocktail of chemicals would be lethally toxic to most forms of life.
And Job, I think it's chapter 38, when God's asking Job questions about the earth that he can't answer. One of the questions God asked Job is, have you walked in the recesses of the deep? Have you seen the springs thereof? And so one of the oldest books that we have in the Bible, we have information there that suggests at the bottom of the deep, the bottom of the ocean, there are deep valleys. And inside of those valleys, inside of those recesses, are springs. And that's what geologists have uncovered. And so God was talking about something that he knew about, but no one else knew about at the time. These hot springs. There's also pillow lavas. As the magma comes through this fracture into the bottom of the ocean, it is very cold at the bottom of the ocean, and so the magma begins to crystallize. The surface forms a hard crust in the shape of a bed pillow. That's the reason they call them pillow lavas. The interior is still molten, and eventually it will push through the crust and form another bed pillow, which will harden. And so it looks like someone took a tube of toothpaste and kept squeezing it. And it appears in layers.
Now the Hawaiian archipelago.
It appears as layers on the ocean floor. This is a video of a pillow lava forming off the coast of Hawaii. You can see the process.
Now the Hawaiian archipelago is expecting again. Loihi Seamount is a volcano that's still 3,182 feet below sea level, but it's growing into islandhood. We can expect it to be out of the water within the next 10,000 years. So have grown, are growing.
So pillow lavas, it's what they look like on the ocean floor, like toothpaste being squeezed out, but it's molten rock being squeezed out on the ocean floor. Believe it or not, there's life at the bottom of the ocean. You wouldn't expect it because there's no sunlight. And if you remember from biology class in high school, the base of the food web is sunlight. Yet you have a whole biotic community which has no connection to sunlight. So how does it get its source of energy? It absorbs it directly from the water column through its skin. These are called tube worms. They can get 12 to 15 feet tall. They're about an inch in diameter. And their body is made of these very fine feather-like extensions that absorb nutrients. That's like their stomach is on their skin, essentially.
1.5 miles down, at a site known as 9 North, towering chimneys support a spectacular display of giant tube worms. These vents give off so much energy that some of the worms reach 3 meters in length. They're the fastest growing marine invertebrates known. All told, over 50 different species have so far...
You can see it's not just the strange alien-looking tube worms, but you also have crabs and fish, eels that are very similar to what we see on the surface, except they have no color. And there's no color because they don't need color. It's pitch black. It's total darkness.
Worms reach. They're the fastest growing marine invertebrates known. All told, over 50 different species have so far been found living here. The inhabitants of these bustling communities may grow at speed, but their existence can also be short, for the vents do not erupt indefinitely. Suddenly, unpredictably, they may become inactive. Nine months have passed at 9 North. What were only recently chimneys teeming with life have turned into cold, sterile mineral monuments. Some eddy deep in the Earth's crust diverted the volcanic energy elsewhere, and an entire micro-world was extinguished.
So if you're at the surface of the Earth, sunlight is readily available. If you're at the bottom of the ocean, you're tied to this one vent, and when the vent changes, everything dies. All right, the ridge system that runs down the Atlantic goes northward, and it comes to the surface here. A little island. You know what this island's called? It's called Iceland. Iceland sits right on top of the vent. As a matter of fact, Iceland was created by the oceanic ridge. So it's a great laboratory for studying the oceanic ridge because you can see it at the surface. This is an aerial shot of Iceland during the wintertime. It's covered in snow. But in the summertime, the snow melts. And you can actually see the layering, this dark band that goes down the middle. That's the most recent volcanic activity, which you see here. And you can see layers in the rock on either side. So you're seeing the older rock on the outside and the younger rock on the inside, just like we see on the ocean floor. There's also a giant rift, a valley that runs down the middle of Iceland. You can see someone built their house there. Not a very good place to build your house. It's called Iceland, although there's not much ice on Iceland. Greenland is covered in ice, but they call it Greenland. I used to joke that that was a realtor trying to sell property, and Greenland was a chunk of ice, so they named it Greenland to get people to go there. And Iceland was really nice and warm with all the volcanoes, so they called it Iceland to keep people away. I was just joking, but actually it's true. They wanted people to move to Greenland, so they called it Greenland, even though there's nothing green on it. There's volcanoes in Iceland. There is some ice, but lots of fire. And at times, the rift will open up and volcanic material will shoot out of it into the air, some cases burying communities under the volcanic debris. From the air, you can see the fractures, the cracks that form. There's even volcanoes along the fractures. Iceland gets almost all of its electricity from geothermal energy. It uses the heat inside of the earth to run turbines that generate electricity. These are some of the electric plants there. So the whole part of the island's being broken up. It's being pulled apart. Even below the ocean surface, you can go down into this fracture And you can see the pillow lavas that have piled up there.
This was the real story of Hayman. Those people had a very nice city with a view on the sea, and then suddenly at night a volcano started to erupt just in their backyard. And this volcano was growing. It was impossible to talk to each other. And we were really attracted by this fire immediately. To see this fire thrown very high into the air was really fantastic.
Those are called bombs. Chunks of rock shooting.
And everything was empty. Icelandic people are not afraid by volcanoes.
So I mentioned the Pacific has a ring of volcanoes and earthquakes all around it. And that's because of the subduction zone. The trench you see here is where the plate is being pushed back into the interior. The highlands here are volcanoes that are forming. And this bump, that bulge, is where the plate is being bent before it's pushed down. If you plot the depth of the focus where the earthquakes occur, you can actually trace out that descending plate. It's what geologists call the Benioff zone. It's discovered by a geologist called Benioff. And they believe that that's measuring the descending plate as it pushes down into the asthenosphere.
Every day, the Earth is shaken by...
Where the rock of the oceanic plate and the continental plate rub together, it causes a buildup of strain. And when that strain reaches a critical point, it releases all of the energy that's been stored, and it creates this sort of bomb under the ground. And as the energy from that bomb goes in all directions, when it gets to the surface, that's what we call an earthquake. So I want to begin now talking to you a little bit about some of the basics of earthquakes.
Every day, the Earth is shaken by hundreds of small earthquakes. Most go unnoticed. They usually occur along the boundaries of the thin plates that cover the Earth like an eggshell. Driven by the heat deep within the Earth's core, the plates grind against each other along lines called faults. When the plates find their motion blocked, stress builds up. Finally, the fault gives way. The released energy races through the Earth in the form of seismic waves. Few natural disasters are as unsettling as an earthquake.
So it's important to reach. Oh, fight!
You know what? Bob made all those, you guys.
There are quite a few earthquakes in Los Angeles because it sits right on one of the largest faults in the earth, San Andreas. And there's a lot of news stations there. So I pieced together some video clips of earthquakes hitting these news studios, and just as a laboratory for how people react. So I thought you might be interested in seeing some of these.
Did you do that? Whoa! Whoa! Okay.
Whoa.
All right, that's an earthquake.
Whoa. Yeah.
And that's a big one.
Wow. Okay.
That is a big earthquake. Obviously, we felt it here at the studio very strongly. I don't know what the magnitude is.
Needed, and then, you know, that was that.
There was no discussion about what he needed.
Okay. Well, he got your credit card, your bank card somehow, and he got your PIN number somehow.
Last year, no home away split, but this year an OPS 65 points lower at home than on the road. So on one hand, getting out of Minnesota would be a good thing, but he simply cannot hit lefties. We've seen this throughout his career. So on a contender, he'd be a platoon player, and that would hurt his value, so you've got to watch out for that.
Hang on. What's going on?
We lost the audio.
No. What's shaking?
Holy shit. Yeah, what's happening? No, the whole room is shaking.
Yeah, the build.
Is there an earthquake?
Is there a building shaking? Should we
get out of
go
here?
somewhere?
Wow. Dude, that's an earthquake.
That was...
I've been in two. That's an earthquake.
That seems to be an earthquake.
Yeah, this is an earthquake.
A lot of people peeking up over heads there.
This is what an earthquake is, guys.
Are we good? I don't know.
Holy shit. Did you know that most of Manhattan is built on landfill?
Yes, I do know
Not
that.
on granite? And if there were like an 8.0 earthquake, then parts of Manhattan would just disintegrate? Did you know that?
I did. I'd like to not be
on one
worried
of those
about that
parts.
right now.
I'll send it back to you.
Ginger, thank you. Coming up, more problems for a troubled
Earthquake.
singer. Yep,
We're
we
having
got
an earthquake. Okay, it appears to have stopped.
Yeah.
We're gonna jump right now to
Look at our cameras behind us.
to the U.S. Geological Survey.
The best way to avoid these email scams... Oh, we're having an earthquake here. Whoa, this is a big one. Wow, this is a earthquake that we just had here at KTLA. Wow.
Goodness gracious, we're not
Sorry,
feeling
guys,
anything
don't know
here.
if you just felt that down there in San Diego. We just had a pretty decent-sized earthquake here in Los Angeles.
Let's get right on that right now. That felt very close.
Very strong.
Yeah, let's get right on that. Okay.
All right, Henry, we're going to bring you into this. You can see right now, I mean, we've got stuff kind of here falling. We've got some sort of ceiling falling from the rafters up here.
Wow, live on the air with you here in the Tech Report. That was
we hear everybody in the back, and everybody okay, Rich?
Aftershocks here as well. Everyone seems to be okay, but there was a lot of shaking here in Los Angeles. Let's see if we can get a number on that earthquake.
Yeah, we're working on it too, trying to get some information.
For 6 years.
It is flooding.
Whoa.
An earthquake.
Big earthquake right now.
Big earthquake.
That's
A really strong shaker right now.
Very big. You can tell we got.
That's
A strong jolt, and it's still
graph right now. This is quite a jolt.
And we can still feel it.
Feeling it.
Well, we're in for another warm day in the tri-state, but it sounds like some rain is on the way. Byron?
Yes, we're hearing some shaking here. It sounds like we have an earthquake here, so I'll have to check that out here. Again, I'm just guessing, or maybe we had some brief gusty. Is it an earthquake? Okay, so we're seeing a little shake here. It's not uncommon. We live here along the New Madrid Fault here. We're at 73 and...
Number 5.
You know what?
Okay, again, I'm just guessing, or maybe we had some brief gusty. Is it an earthquake? Okay, so we're seeing a little shake.
It is true that gusty wind can shake buildings if you're near the top. Could feel like an earthquake. In terms of damage, and death associated with earthquakes, it's important to realize that shaking doesn't kill people. Buildings kill people. So the question, should we be going somewhere? Should we be doing something? Yes. If you can get out of the building quickly, you should get out of the building. If you're on the lower floor near a door, get outside. If you can't get outside, if you're in an upper floor or you're not near an exit, then try to find something that's fairly stable and get under it. All right. So for me, where would I want to go? I would want to go under here. Matter of fact, there's probably enough for all three of us to get under this desk. This is the most sturdy desk in the room. So we would pack together on this desk. So when the ceiling fell, it would hit the desk and we would be okay. Underneath these desks could be a little bit better, or would be the next choice. If there's no desk for you to get under, then stand in a doorway, because the doorway is usually reinforced. And when buildings collapse, many times the doorways will stay intact. And so that's your next best choice. Try to get in the fetal position, put your arms and legs inside, huddle up so that your visceral organs are more protected. All right, so I know that sounds bad, but when that does happen, you need to know those things so you can increase your possibility of survival. All right, my voice is just about gone. I've got another class today and a class tomorrow too, so we're just going to stop there. And so we were looking at the oceans that surround the Earth. First, the ocean of magnetism called the magnetosphere. And then below that, the ocean of air, which we call our atmosphere. And within the ocean of air, there are different layers. The thermosphere, also called the ionosphere on the outside, then the mesosphere, then the stratosphere that we've heard talk about, and below that, the troposphere, where weather takes place. We spent quite a bit of time exploring the atmosphere and all the different weather patterns that occur, hurricanes and tornadoes and so on. Even things like lightning and meteors and UFOs and so on. Then we dove into the hydrosphere, the ocean, and talked about some of the aspects of our ocean currents, surface currents, deep ocean currents, and so on. And now we're in the lithosphere, the ocean of rock below our feet, and talking about some of the characteristics of the ocean of rock. And we began discussing last time earthquakes. I want to go into a little bit more detail today and talk about some of the basic elements of the study of earthquakes, which is called seismology. Before we do that, though, let's pray for a second. Father, we thank you for your great grace, for loving us the way that you do, Father, for providing all of our needs according to your riches. We give you praise, Father, for each breath, each heartbeat, recognizing that it is a gift from you, and pray that we would use it for your glory. Thank you for these students, Father, and their desire to come and to learn more about the world that you've made for them. I pray, Father, that you would help me to do my very best, not just to show them the world, but to help them understand more about who you are and your majesty and your wisdom and your power. Father, we pray that you would preside over our class today, that you would teach us the things you want us to know, that we would be yielded, Father, and teachable, and that through the power of your Holy Spirit, you would help us to take the information and live it out to build your kingdom and to glorify you. And we pray this in Jesus' name. Amen. All right, what is an earthquake? An earthquake is where there is a fracture, a break inside of the earth, which is called a fault. And along that fault, because of the stresses and strains, energy builds up. It sticks, as they say, and eventually the energy is so large it overcomes the frictional force holding it in place, and it slips. And so geologists often call that stick-slip motion. Another term they often use is elastic rebound, that the energy is actually stored in the rocks as it sticks, and whenever it slips, that rebound of energy creates an explosion inside the earth.
like a nuclear bomb going off. As a matter of fact, the signatures for nuclear bombs and earthquakes are very similar. We've learned that there are differences we can detect, but for the most part, they're very similar because an earthquake is like an explosion below the surface. The place where the explosion occurs, in the old terminology, was called the focus. A more modern term is the hypocenter. You can see it here in the diagram. At the bottom of the image, where the energy is released, is called the hypocenter. Directly above the hypocenter, where the energy first reaches the surface, is called the epicenter. And the term epicenter is probably the phrase or the term you're familiar with. You've heard it, the epicenter of the earthquake was somewhere in Irving or whatever. That is expressing where the energy first reaches the surface. So in this explosion, waves move out from the explosion, like when you throw a pebble in a pond and you see the waves moving across the surface. Same thing happens inside of the earth. There's concentric rings of energy that radiate out from the focus or the hypocenter. You can see that here in the diagram as it's reflected. There are two basic components to these waves, seismic waves, and seismologists refer to them as P waves and S waves. And in this diagram, you can see that they've tried to demonstrate what a P wave is and what an S wave is by showing the direction in which the particles are moving as the wave progresses. So a P wave, the P, actually, the letter P can stand for two different things, which help us understand the basic components of the wave. It could stand for pressure as a pressure wave, which it is, which means that the particles are being pressed together and then released. But the P also can stand for primary, because a pressure wave is very efficient in terms of moving energy. It's fast, it moves very quickly. Therefore, it will move from the hypocenter to the seismograph that's measuring, the instrument that seismologists use to measure earthquake waves. It will move very quickly and will arrive first. That's the reason they call it primary, because it arrives at the seismograph first. The S wave is different. The S can stand for shear wave, which means that the particles are shearing past each other, not pressing against each other, but shearing past each other. That's an inefficient way to move energy. Therefore, they're slower. And so they arrive at the seismograph second. So they're often referred to as secondary waves. So it works out really great with the lettering there. P for pressure, P for primary, it's faster. S for shear, S for secondary, it's slower. We're familiar with these types of waves, the basic concept of the wave anyway. If you remember when you were in grade school standing in line at the cafeteria, you guys still do that? When you go to the cafeteria, stand in line? And so you're standing in line waiting for whatever the mystery meat is that day in high school. And then someone in the back of the line pushes someone else. And so as the bodies move forward, they press in to the body in front of it, then it's released. And so if you looked at a pressure wave, the wave is actually moving in the same direction that the particles are moving. So the people in line are moving front to back, front to back, front to back, and the wave is moving from front to back. That's a very efficient way to move energy. It's quick, so it gets to the seismograph first, therefore it's the primary wave. Now, a secondary wave would be like doing the wave at a sporting event, where you're sitting on the bleachers and you're looking to your left and to your right, and you're seeing the wave coming and trying to move up at exactly the right time. So as the person next to you begins to move up, you wait until they're moving down. As they're moving down, you move up. And so if it's a really crowded arena and you're all smushed together, then as you're moving up and down, you can actually feel that shearing that's occurring between your bodies. You can also see that your body as a particle in the wave is moving up and down, but the wave is not moving up and down. The wave is moving left to right or right to left. And so in a shear wave, the particles are moving in a direction perpendicular, 90 degrees from the way that the wave is moving, which is an inefficient way. Matter of fact, the shearing motion actually pulls energy out of the wave and slows it down. Therefore, It's secondary, and it gets to the seismograph later. Any questions on the basics there of P waves and S waves? Because they're moving through the body of the Earth, they're classified as body waves. I think that's a test question. What are the two body waves? P waves and S waves. Why are they called body waves? Because they move through the body of the Earth. Once the energy reaches the surface of the Earth, it spreads out across the surface as a surface wave. And so if you look at the diagram there, you can see whenever the energy gets to the surface at the epicenter, you can see the waves moving out from the epicenter. Some cases, in very severe earthquakes, you can actually see the waves on the surface. They're not like waves on the ocean. You would look at a house on the horizon and you see the house begin sinking down as you rise up, and then you would sink down as it rises up. So the wavelength of these surface waves may be 3 or 4 miles, yet they are still waves on the surface, and they're the slowest waves, and so they arrive later. Geologists have developed different instruments throughout the millennia to try to determine the magnitude and the direction of these seismic waves. Some of the earliest were simple jars that had little frog mouths on the outside with marbles sitting in the frog mouths, and they would set this jar with the balls balanced very delicately in the frog's mouth on all the different sides of the jar on the center of a table. And whenever there was an earthquake, the jar would rock back and forth, and it would kick the marbles out of the mouths of the frogs in which direction the wave was moving. Very, very primitive, as you might imagine. Now we have much more complex seismographs that can measure the magnitude and the direction of these waves. The basic principle that they use now is by creating a stable platform in the Earth's gravitational field and allowing the Earth itself to move independently of that stable point. One of the best ways, I think, to describe it is if you could imagine that I'm holding a string, a thread, a magic thread, and attached to that thread is a 700-ton lead weight. And I'm very strong, I have very strong biceps, so I'm able to hold it up. And I took that string and I moved it back and forth really fast. Would the weight move? No, the weight would not move because that's 700 tons of weight. So the movement of this little thread is not going to change the position of this massive lead weight. So now imagine, rather than me moving my hand back and forth, that I move the whole building back and forth. The whole building is rocking back and forth. The lead weight is still suspended in midair. The lead weight is still not going to move. It doesn't know that the building's moving around it. It's just suspended within the gravitational field. Now let's assume that I put a pin on the bottom of that lead weight, and the pen has ink that's setting on a piece of paper on the floor, and now I move the whole building. Well, as I move the whole building, what that pen is going to do is it's going to draw a series of squiggly lines on that piece of paper. And those squiggly lines will not only show which way the waves are moving, but it gives an idea of the magnitude, the size of the wave by how squiggly the squiggly lines are. So if you look at this image here on the screen, you can see the record that was produced from the seismograph. This is called a seismogram. I know it's probably not important to you guys, but scientists like people to use their terminologies correctly. So the seismograph is the instrument. The seismogram is the paper record that comes off of the seismograph. And this is what it looks like. You can see the ink is being drawn across the paper. And then whenever the earthquake wave first occurs, you see this kick. And you get an idea of the size of the kick. When that kick first occurs, seismologists call that the first arrival. So that's the first arrival of the P wave. And you see it diminishes. So the initial wave is the strongest. It's like when you throw a pebble into a pond, you get a series of ripples. That first ripple is always the largest. So that's the first arrival of the P wave. and then time passes, then you see another kick here. That's the first arrival of the S wave. The secondary wave is coming in behind it, and then behind that, you can see these very large kicks. Those are the surface waves. So body waves, P wave and S wave, and the surface wave. Based upon the distance or the time between the first arrival of P wave and first arrival of the S wave, the geologists, knowing the density of the rock and how fast the waves move through the rock, they can calculate where the epicenter is, how far from the seismograph the epicenter is. And once they have 3 of these readings, they can triangulate and actually discover the location of the epicenter. It's not like there's a sign pops up at the surface that says the epicenter. You have to calculate these things. This is a record of the earthquake that hit Mexico City in the 1980s. And you can see the squiggly lines here that form the surface waves. You see this is a very large magnitude earthquake. And then after that, you can see a series of what they call aftershocks occurring after the major quake. This is showing a series of seismograms. The lower seismograms are closer to the earthquake. The upper seismograms are further away from the epicenter of the earthquake. And you can see the first arrival of P wave and S wave. See how it's getting wider? That gives us an idea of how far away from the epicenter the seismograph was. It would be like if you had a race between a supercharged turbo Corvette with a 16-cylinder engine or something, and then you had a race between that vehicle and a Volkswagen Beetle with a bad carburetor and low tire pressure. And you had a race. You could tell how long the race had been going by the larger the gap between the two vehicles. Same way with the seismograms. The P waves is the Corvette, and the S wave is the Volkswagen Beetle with the bad carburetor. And so you can see how long the race has been going. All right, let's talk about the faults themselves, the fractures inside of the earth. One of the most famous of all faults, especially in the US, is the San Andreas Fault in California. It actually marks the boundary between two plates, North American plate and the Pacific plate. And this is what it looks like over the years. The movement along the fault have created a fracture you can see at the surface. Just a second. Get this set up.
Testing sites on the American continent, the San Andreas Fault. I hope we're going to be able to see the fault. At this time of day, everything looks beautiful.
This is nice. Dry, oh yes.
The San Andreas Fault, where 2 tectonic plates bang together.
It's nice, huh?
On the left, you can see the American plate. On the right, the Pacific plate. These underground forces are impressive. The rock is crumpled like tissue paper. Sites on the American continent.
So that's a very large fault. Actually, most faults, though, are not that large. They're smaller splay faults. You can see evidences of one here. The tree, this large tree, it's been a few hundred years growing along this fault. And during an earthquake, as the fault moves, you can see it took that giant tree and split it right down the middle. Same thing happens in fields that have been plowed. You can see the fault as the lines, the rows there, the plowed rows have been displaced. When they talk about the displacement, the movement along a fault, they have 4 different ways of describing it. Whenever the blocks move laterally past each other, like you see here, that's called lateral displacement. Whenever the blocks move up along the fault, that's called vertical displacement. Whenever the 2 blocks pull apart, that's called extensional displacement. And when they come together, compress, that's called compressional displacement. Okay, so this would be lateral displacement. Here's another example of lateral displacement. You can see when they planted these orange trees, they formed nice even rows. And after the earthquake, you can see how the rows have been displaced here, and that marks the fracture, the fault. Here's another example of lateral displacement, where the stream valleys have been moved. During an earthquake, they may only move a couple of feet at a time, but over the centuries and many earthquakes, you can see that there's probably a good, 100, 200 feet of displacement along this fault. Here's another fault where you can see layers of rock that have been displaced. This is a good example of compressional displacement. In other words, the blocks have been pushed together. You can see these lobes of material. As they're pressed together, this material is forced upward. Compressional. Here's an example of lateral displacement. Matter of fact, train tracks, because the iron in the track is very flexible, you can see the effects. And you can get an idea of how far the blocks have moved, because you imagine that the train tracks before the earthquake occurred were nice and straight. They didn't bend like this. And so the fault is right here. Lateral displacement, at one time, the train track was even. So the side of the block we're standing on has moved from a position here, this rail, from here, it's moved all the way to this area, and then it's moved back. So it's like taking 2 steps forward and 1 step back. 2 steps forward, 1 step back. You can get a sense of the motion of the rock. Once again, this is the fault. You can see the train tracks are almost even again, and so they've moved. It looks like the side we're standing on has moved to the right and has come almost back to its original position. The train tracks are very good at giving us an indication of how the ground has moved, not just where the fault is, but how much displacement has occurred. All right, so examples of lateral displacement, showing where the faults are. And it works with fences too. Example of compressional displacement. The expansion joint there in the sidewalk has caused the units to just stand upward like dominoes. This area was compressed, putting it in a big vise. This is an example of extensional displacement. It's been pulled apart. We often think of that in earthquakes, that the ground opens up and swallows people, which sometimes it does. When you have, especially when you have extensional followed by compressional displacement, it can open up and swallow people. This is an example of vertical displacement. The fault is here. The right-hand side has dropped down about 20 feet. This is in Anchorage, Alaska, after the 1964 Good Friday earthquake. I've been told that they didn't try to correct this. They didn't tear everything down. They just built a wall here, and you have to walk down the steps to get to these other shops. The Good Friday earthquake in Anchorage, another example of vertical displacement that split this school right down the center. Another feature of earthquakes is something called liquefaction. I'm sure you've experienced liquefaction. If you've ever been to the beach and you stood right at the swash zone where the waves are coming in and you wiggle your toes, how your feet will sink into the sand. That's the process of liquefaction. The movement actually causes the grains of sand to readjust. And as they readjust, it becomes for a moment sort of like quicksand. And it's very fluid and mobile. Well, whenever an earthquake occurs and it moves through a particular region, it does the same thing. The vibrations can cause the liquid to begin moving out of the grains and supporting the grains. And so it becomes sort of a slush. And the compressional forces of the earthquake can cause that slush to shoot out at the surface in what geologists call a mud volcano. So you see this mud, how it comes from the hole there at the bottom and just spreads out. This occurred during an earthquake when the liquefied sediment just shot out at the surface like a volcano. Not even with earthquakes, but whenever you have trees and the roots go down into the soil and there's a wind and the wind is causing the trees to move back and forth, it can cause the area to become liquefied and very, very mobile. I had heard about it, talked about it in class, but I didn't have a video evidence of it. And then I found this on the internet. It's a GIF showing the liquefaction in this forest. See how the ground is just moving up and down? It's because this ground has become a muddy slush. Why is it a muddy slush? Because the wind's blowing these trees back and forth, and as their roots move underground, it's causing liquefaction. The damage that's caused by an earthquake is controlled many times by the construction methods that are used in building the structures. If you have a structure that's fairly flexible, it will withstand even large earthquakes. So materials such as iron, steel, glass, they give and bend. Materials such as concrete and masonry, brick do not give very well and oftentimes will collapse. This is an aerial photograph of a village in Africa, and the buildings there are made out of adobe. They're made out of sun-dried brick, which is not very flexible at all. And so whenever an earthquake occurs, it goes from this to this, which all of the houses have completely collapsed during the earthquake. Recently in Turkey, there was an earthquake, a devastating earthquake. And many of hundreds of thousands, I think it's close to 100,000 people now are estimated to have perished in this earthquake. And the main reason was because of the building codes. This is a very disturbing image of one part of Turkey that was destroyed. You see the building that has very little damage at all? That building is a building for civil engineers. So the civil engineers actually built their building with correct methods, and it survived the earthquake. But all around it are other buildings that were not built using materials that would give and construction methods that would hold them together. This is a road in Turkey. And you can see how the blacktop has been ripped up, and you can see underneath the blacktop is absolutely no subbase. Whenever you build roads, you're supposed to add layer upon layer of material below it to help stabilize the road's surface itself. Whoever built this road just poured blacktop right on top of sand. And so, yes, that's when you use cheap building materials, that's the kind of destruction you would expect. Even in well-developed areas such as San Francisco, areas which they know are going to hit by earthquakes, they still make mistakes in construction methods. This particular highway, it's a double-decker highway called the Nimitz Freeway in San Francisco. And whenever they built the buttresses, the pilings on either side to hold up the upper deck, they didn't allow for lateral displacement, movement back and forth. And so those buttresses gave way and the upper deck collapsed on the lower deck. Matter of fact, over half the deaths from the 1989, I think it was, earthquake in San Francisco were from this one section of the highway that was poorly constructed, the Nimitz Freeway. Earthquakes don't kill people, buildings kill people when they collapse. Therefore, construction methods and the use of flexible type materials, reinforced materials, are very significant. Just images from the Nimitz Freeway. After
Structures like bridges and freeways are especially vulnerable to tremors. In San Francisco's quake, most of the deaths occurred on the Nimitz Freeway when a 1.5-mile section of the upper deck collapsed on the roadway beneath. Ed McVie was driving a freight truck when it happened.
There was no traffic, and I was doing about 55, and all of a sudden it felt like I had a blowout. I had no control over the truck. Luckily, there was nobody beside me because I was just all over the place. I hit the brakes. In the rearview mirror, I could see what looked like the freeway falling, and that didn't make any sense. I saw cars and trucks disappearing underneath the rubble, and I just knew I was dead. I had no way of getting out of it. There was nothing I could do.
McVie was lucky that day. His truck just happened to stop under the only section of freeway that didn't fall.
I don't deal with it as well as people think I do. I can be driving along anywhere, and all of a sudden I've got freeway falling down on top of me.
Ed McVie escaped without a scratch. 42 other motorists died.
This is a photograph taken in Mexico City after the Mexico City earthquake in 1985. The epicenter for the Mexico City earthquake was actually out in the Pacific Ocean. One of the reasons there was such devastation in Mexico City is because the city itself was built over a lake. According to the history of Mexico City, it began as an Aztec city on an island out in the middle of the lake. And as that Aztec city began to grow over the lake, that was built on top of very loose, unconsolidated gravels and sands of the lake. And so when you go to Mexico City, the downtown area is actually built over very unconsolidated, loose materials of this old lake bed. And in 1985, when this distant earthquake moved seismic waves through the area, it caused that lake material to shift, to settle, and all the buildings collapsed. You can see here they fell over, or they pancaked down on top of each other, and the people inside the buildings were killed. It's like when you're cleaning out the closet and you're putting stuff in boxes and need more room in the box, so you shake it. And when you shake it, it settles. Well, the lake bed settled with this earthquake. This is a heartbreaking photograph. Each of those cement beams there represent a floor of a hospital. This is about a 10 to 11 story hospital that has just collapsed one layer down on top of the other. I think I was reading that over 1,000 people died just in this one hospital. I mentioned San Francisco earlier. This is an aerial view of San Francisco Bay. And if you look carefully, you can see these long linear features here and here. That's the fault, the San Andreas Fault. And so the fault itself has created this very picturesque bay. And the people of San Francisco have built their city right on top of the fault, which is not a very smart thing to do. You should build away from the faults. They understand from ancient records going all the way back to the 16th century from Catholic missions in the area that there's a major earthquake along the San Andreas Fault about every 80 or 90 years. There was a major quake in San Francisco in 1906. So we'd expect about 80 years later, there would be another major quake, and there was another quake in 1989. So it's following that same pattern. It's part of the stick-slip motion. It takes about 80 years for enough stress to build up on the San Andreas Fault for another major quake. These are some photographs that were taken after the 1906 earthquake. This is in Sacramento. It shows the Capitol there, the cupolas that's fallen. This is from San Francisco itself. That's a statue of Louis Agassiz that's done a head dive into the pavement after the initial quake. Pictures of dead horses from the carriages as the facade, the brick facades of the buildings collapsed into the street, crushing the horses. Even though the San Francisco earthquake was devastating in terms of the physical damage of the original quake, that's not what destroyed San Francisco. Only a tiny fraction of San Francisco was destroyed by the quake itself. What destroyed the whole city, though, was the fires. And the vast majority of damage from earthquakes is caused by the fires that occur in urban areas. This is a photograph that was taken of one of the streets of San Francisco in 1906. You can see the fire trucks here that have some water pressure to try to put out the fire. The problem was that the water mains had been broken by the movement, and gas lines had been broken. And as these structures filled with natural gas, any spark caused them to catch on fire. And once they caught on fire, there was not any water pressure to put out the fire. And so the people of San Francisco for several days just stood in the streets and watched their city burn to the ground. As you can see here, after the Great Fire, hardly anything was left. I think there are a few Victorian homes that survived. But anyway, these are photographs taken as San Francisco burned after the 1906 earthquake. So it went from this to this. All of the buildings were collapsed and raked into San Francisco Bay. They created a large amount of real estate in the San Francisco Bay that's called the Marina District. That was built upon the rubble of the old San Francisco. Anyway, you can see even the large churches and cathedrals were destroyed by the fires. I think that's a test question. Most damage of earthquake is caused by fires. And San Francisco is the prime exemplar of that truth. Yeah, here are a couple of Victorian homes that survived the fire, and you can visit them today. It's one of the few pre-earthquake structures remaining in San Francisco. In 1989, when an earthquake hit San Francisco, most of the damage was in the Marina District. Just somewhat ironic that people had built their houses over the rubble. And as the rubble from the 1906 earthquake settled, it caused history to repeat itself. Gas lines are broken, and electrical lines caused sparks that set the Marina District on fire. And because of the broken water mains, once again, firefighters had to sit there and watch the Marina District burn. The building on the left is made out of concrete. Building on the right is made out of steel and glass. They're right next to each other, so they experience the same amount of ground motion, but you can see the vast difference in destruction. So it shows very clearly that flexible materials survive earthquakes, glass and steel. Even though we often don't want to think about being cut by glass, you're probably much safer in a glass building in an earthquake. And, you know, medical doctors will tell you if you're going to have an injury, lacerations are much better than some kind of crushing wound where your bones and things are crushed. So yes, steel and glass. I think there's a test question where I ask you where you would like to be during an earthquake, and that's going to be one of the major components in answering the question is to think about, are you in a place which is flexible and built on a strong foundation? Because most damage is caused by poor construction materials that do not flex and having a very poor foundation. Whenever there is displacement, movement along a fault in the ocean, it causes a sloshing, just like if you were to slip in the tub, you would create a wave. It would wash out over the bathroom floor. Whenever the rocks slip below the ocean surface, they also create a sloshing, a wave in the ocean itself. The Japanese call them tsunamis, which basically just means a seismic sea wave. This is a image that shows the sea wave, the tsunami that was produced by an earthquake in Washington. You can see how the waves have moved across the Pacific and all the smaller waves that are produced as they move through the different island systems. That's just the first initial wave. The wave will return and it'll move out again. So there's a series of waves that come from these earthquakes, tsunamis. And the islands in the Pacific, they have ways of measuring them. So when there is a tsunami, they can not only determine that there is a tsunami, but which direction it's moving, and they can warn people along the coast and tell them not only that it's going to occur, but when it's going to occur, so they can begin moving out of harm's way. When we think of a tsunami, we often see some kind of big breaking waves, such as you see here. This is all photoshopped. This is not what a tsunami looks like. It's not a big breaking wave. When the water comes in, it's actually a giant mound of water that rises like a rise in sea level. So you can't surf a tsunami is what I'm trying to say. Here's a photograph taken of a tsunami approaching Hilo, Hawaii. And you can see it's just a giant mound of water. The beach is down here somewhere. This is about a 40-foot mound of water that's just moving inland. It's another photograph of the same tsunami near Hilo. In this case, you can see what's left of the docks in the foreground that are riding on top of this big mound of water. There's a person right here to give you an idea of scale. And so this person's 5 or 6 feet tall. You're looking at probably about a 30-foot, 25, 30-foot mound of water coming in. This guy's in big trouble, as you might imagine, because this wave is carrying debris. I don't think they ever found him. Whenever, before a tsunami hits, the wave will pull the water out, generally for about 20 to 30 minutes. And it'll pull it out in some cases a quarter to a half a mile. So if you're ever standing on a beach somewhere and the water begins to retreat very quickly, it begins to pull out to where you can look maybe a quarter of a mile out and it's all sand. You shouldn't stand there, and you definitely should not walk out onto the sand. You should turn around. You don't have to run, but you should walk very rapidly inland, trying to get at least a quarter to a half a mile inland, and then try to get high up into a building. And to tell people around you, they also need to move inland, because if the water pulls out that far, there's probably a tsunami coming in, and you have about 20 minutes to get out of harm's way. These guys you see in this picture didn't do that. They stood around on the beach, and see what's happening? That's about a 20-foot mound of water coming at them, and now they're not able to outrun it. Tsunamis in the open ocean can reach 150 miles per hour in terms of their movement. They don't move that fast when they come on land, but they are moving much faster than you can run. This is what it does to parking meters. You can imagine the lifting water pulls up boats, carries the boats inland, parking them in people's houses. This is an aerial shot of the pull out of the water before the tsunami that hit Thailand and India. This is a ground level shot of that same tsunami. These people are not doing what they're supposed to do. They're standing there watching the initial wave come in. They've been standing there for about 15 minutes. You can see the initial wave coming in. Someone has even gone way out into the surf. You see that guy? Big trouble. That's a 40-foot wave that's coming right at him. When the tsunami hit Thailand, I remember they were interviewing a girl. She was probably 12 years old or so. She just had earth science in junior high. And she had learned about tsunamis. The teacher had told her the same thing I'm telling you guys now. And she was in Thailand, and when she saw the water pulled out, she told her mom and dad, we need to get inland and tell everyone else. And so they went up and down the beach, telling everyone to run inland. And they think that little girl's knowledge may have saved close to 200 lives along that beach compared to other areas because they knew what to do. So the water pulls out and then it rushes in. It moves not only over land, but it moves up rivers. Matter of fact, the devastation of a tsunami could move half a mile inland along the beach, but when you're near one of these rivers, it can go 6 to 7 miles up the rivers, causing damage. Whenever the water pulls out, after the initial wave, it will interact with other waves coming in, and it creates these strange whirlpools, eddies. The whole process is extremely devastating, not just because of the water itself, but all the debris that the water is carrying acts like a giant rasp and just bowls everything over in its path. This is an aerial shot before, this is after. See the devastation? Before, after, before, after, before, after. It just scrapes the ground. As you know, southern Japan was hit by a massive tsunami, not 20 feet high, but in some areas over 100 feet high. The epicenter for the earthquake was just right offshore, so they had very little time to prepare. This is an aerial shot showing that initial wave coming in and washing over the seawall and moved inland about half a mile to a mile. As you might imagine, it was recorded on many, many video recorders, digital recordings. Back when, about 6 months or so after the tsunami hit, I went on the internet and YouTube and I gathered as much of the video as I could, and I pieced it together into about a 10-minute demonstration of what it's like whenever a massive tsunami hits the coast. And I'll play that for you in just a second. But in the still images, you can see you have houses that are ripped off their foundations. You can see the whirlpools that are created as the initial wave pulls back out and impinges upon incoming waves. It creates these vortices, these maelstroms. All right, this is the video clip. The first will show a diagram showing the fault and the earthquake. So before the tsunami came in, parts of Japan were destroyed by the earthquake itself, and then the tsunami followed after. So below the ocean surface is a fault, part of what they call a subduction zone. The stresses build up, stick, slip fashion, and when it's released...
Shocked supermarket shoppers tried to stay on their feet. Airport travelers dodged falling debris. And a TV crew setting up for an interview was suddenly interrupted. In Sendai, the city closest to the epicenter, books flew from shelves. Debris from buildings crashed to the ground. As pedestrians, the quake lasts 5 agonizing minutes.
It was so significant that I couldn't stand up in my room. That's how much the building was moving at the height of the main quake that hit.
Okay, so first the earthquake and then the tsunami. As the energy is released, it creates vertical displacement on the ocean floor. That creates a wave. So the surface rises and it spreads out from the epicenter. This is just showing how the wave disperses from Japan across the Pacific.
Matt, tell us about the situation for you when this magnitude 8.9 hit.
Well, it was absolutely unlike anything I've ever experienced before.
So this is the water that's retreated, pulled out.
Tsunami.
And that's the leading wave coming back in.
Komm, wir müssen los.
So you can see it's not one large breaking wave. It's actually a giant mound of water. You may have a series of breaking waves on top of it. Most often, though, it's not breaking waves. It's just white caps. It's just the turbulence of the water itself. It might look like just a very large sea wave, but the difference is that it doesn't stop. It keeps going. See how dark it is. That's from the mud that's been ripped up off the soil. When it hits the seawall, it goes vertical for a while. There's the seawall. That's the initial wave. Then it goes over the seawall and continues through the trees. By the time it's made it to, 1/8 of a mile inland, the water looks like chocolate milk, like a malt. It's just completely saturated with debris and soil. And it pulls up even more. Matter of fact, that's what eventually ends the tsunami, as it just becomes so thick, the friction will stop its forward progress. But not before it does tremendous damage. It's a helicopter image of that initial wave. Continue to move inland, carrying houses and boats, debris that it's ripped up from the fields.
Those of you who have just tuned in and living anywhere close to the coastal areas of Russia, Marcus Island, Northern Marianas, Guam, Wake Island, and Taiwan,
they're warning other
please
beaches that the tsunami's coming.
the waters. Move to higher ground.
It's not nearly as devastating as in Japan because it was so close to the epicenter.
You're watching NHK World, and a major earthquake hit Japan Friday afternoon. This happened about an hour and 20 minutes ago. Japan's meteorological agency says the quake measured magnitude 8.4. The agency has issued a tsunami warning for Japan's Pacific coast. In northern Japan's Iwate Prefecture, tsunami waves of up to 4 meters were observed soon after the quake. The agency is warning that the tsunami could be between 6 and 10 meters.
大丈夫？
Water continues to come in. The sea level rises eventually over the top of the building. See it here.
いや、ちょっと危ないじゃん、本当に。あー。わー。
Where there were inlets on the southern part of Japan, the tsunami was focused and reached over 100 feet high. Most areas it was 40 to 60 feet. You can see as it moves through the buildings, it actually picks up the buildings and uses them like battering rams to smash other buildings in its forward motion. So the buildings there in the foreground are being battered by the other buildings. I think this is the area where it reached its maximum. Where there are rivers, the tsunami focuses along the rivers, and so rather than a mile or so, it can go 6 or 7 miles up these rivers, flooding as it goes. All right, any questions on tsunamis? There is another feature associated with ocean waves called rogue waves. And when you see images of these very large breaking waves out on the open ocean, they're often called tsunamis, but that's not what tsunamis look like on the open ocean. However, there is a phenomenon called a rogue wave where you can have a freak combination of several different wind currents that can create a very, very large standing wave out on the open ocean. They can be 2 or 3 times as large as storm waves. The difference is with a rogue wave is there really isn't a storm. It's just a giant wave that suddenly appears out of nowhere. It's one of the reasons cargo ships that you see traveling the open ocean are often built completely enclosed, because when they approach one of these rogue waves, they actually have to become a submarine for a while and go through the wave. Anyway, this is an aerial shot of a rogue wave. And some photographs that were taken of these cargo ships that are headed into these large waves that may be 50 or 60 feet high, that just appear on the open ocean. The rogue wave will eventually reach shore. Sometimes they can run out of energy where they're not that big. Other times, when a rogue wave does reach shore, it is like a mini tsunami. This is a couple that are enjoying a beachside cafe when a rogue wave hits the window there and breaks through and ruins their lunch.
That's a big one. That's a big one. Oh, damn. Oh, my God.
This is a surfing competition that was really disrupted by a giant rogue wave. And a family swimming along the beach in the fairly large sea waves, and then a rogue wave comes in on top of them. However, it's not a tsunami, because you can see, even though it was a large wave, it flows back out to the sea. Tsunamis don't do that. They just keep going. This is a freak accident where a rogue wave actually came in on top of high tide. So you not only have, the 40-foot rogue wave, but then you can add probably another 4 or 5 feet just because it was high tide, and caught these people off guard.